Okay, covalent bonds. So if we're looking at Lewis structures for molecules, we're going to show neighboring atoms sharing electrons to get octets, or for hydrogen, a duet. So we're going to use Lewis structures to show the bonding in water and chlorine. So H2O, let's look at the two elements there. We've got hydrogen, we've got oxygen, we've got hydrogen. How many valence electrons does hydrogen have? It has 1. How many valence electrons does oxygen have? 6. I'm putting pairs on the top and singles on the sides because it's going to line up better for what I want it to do. That's the only reason. So oxygen would like to get 2 electrons, but the hydrogen isn't willing to give up the electron. Nobody wants to give up what they've got. So that's when you have to share, right? That way you can both use it. So what happens then is that this oxygen and the hydrogen decide to each share 1 electron with the other. And this oxygen then also shares an electron with the other hydrogen. When you're sharing something with someone else, those shared things belong to both of you, right? So when hydrogen goes to count its valence electrons, it's like, I've got 2. I've got these 2 electrons that are shared between me and oxygen. 2. That's good. That's all hydrogen wants, is 2 electrons. And the oxygen here now has these 2 electrons and those 2. That's 4. And then it also counts these electrons, and it counts these electrons, right? So oxygen says, hey, I've got 8. Awesome. And the other hydrogen says, I'm good too, I have 2. So the electrons go farther because they're being shared. So my husband and I have 6 children. And if you ask him how many kids he has, he'll say he has 6 kids. You ask me, I'll say I have 6 kids. Are there 12 children in the house? Thank goodness no. It's the same 6, right? They belong to him and they belong to me, so we both count them. So these shared electrons belong to oxygen and to hydrogen, and so both of them count them as their own. So we can count electrons double, and so we can get octets or duets for everybody, even though there doesn't seem to be enough electrons. Any questions? So let's see how that might work with chlorine. So Cl2 is a molecule. Good enough. How many valence electrons? 7. 1, 2, 3, 4, 5, 6, 7. And this one also has 7. 1, 2, 3, 4, 5, 6, 7. Neither is willing to give up an electron, but they're willing to share. So if they each share 1 electron, then they each have now 8 because they count the shared electrons. Right, so this chlorine is looking at all of these. Those are mine. And the other chlorine is looking at all of these. Those are mine. They both have 8. This is a good way to do Lewis structures when you're first starting, to show them as dots connected. But normally how we would show them later is we're just going to put a single line for that single bond, and then we're going to put the other electrons in as dots. And so chlorine would be like this with, oops. And when we look at this bond, this line, we understand that's a pair of electrons being shared. And so You know, when you're still getting used to what this is looking like, you might want to put the dots on there. Just to remind yourself, oh, yeah, that's 2 electrons. So then this also asks us to identify bonding pairs and lone pairs. Lone pairs are non-bonding electrons. Well, let's find the bonding pairs first. Where are the bonding electrons in water? They're in the bonds, right? So there's 2 electrons in there, and there's 2 electrons in here. Those are bonding electrons. They're being shared. In the chlorine, the bonding electrons are in the bond. And then the non-bonding or lone pairs, those are the electrons that are not in bonds. And so there's a pair up here and a pair down there, and they're not between the oxygen and anything else. They're just hanging off oxygen all by themselves, right? It's a lone pair. And over in the chlorine molecule, there's a whole bunch of lone pairs. Each chlorine atom has 3 lone pairs. So lone pairs and bonding pairs.
So if we're asked that, how would we do it if we don't have colors?
That's a good question. Because, the exams, we don't have colors. So they would ask you something like, how many lone pairs in this molecule? How many lone pairs? And so you'd say 1, 2, 3, 4, 5, 6. 6 lone pairs and 1 bonding pair. Great question. Anybody else? We need to be able to count lone pairs and bonding pairs for some things we're going to do later. Well, you can share more than 1 electron with the other atom. You can share more than a pair. So let's look at oxygen. So the oxygen molecule, O2, 2 oxygen atoms. We've discussed this already. They each have 6 valence electrons. And again, I'm putting them in like that because I know what I want to do with them. So each of these atoms has 6 electrons. They want to share so that they can each have 8. So we can make a bond here between those 2. This oxygen is going to share 1 electron with the other oxygen, and here this one's going to share with that one, and so we have a shared pair, a bonding pair. Now they would each count 7 valence electrons, which is better, but it isn't 8. So we need to share more. So we're going to take these other electrons and share those also. So this is 2 pairs of shared electrons. So instead of a single pair of electrons, it's a double pair. And so we call this a double bond. And it's represented with 2 lines, 1 line for each shared pair of electrons. So in oxygen, how many lone pairs are there? There's 4 lone pairs. 1, 2, 3, 4. How many bonding pairs? 2 bonding pairs. Okay. So this is a double bond. Nitrogen forms a triple bond. That's what my husband and I have, is a triple bond. So each of these has 5 valence electrons. So they're going to have to share a whole bunch, right? So share these. So now we've each got 6. Let's share some more. Now we each have 7. Let's share a third one. Now we have 8. And so that's kind of strange looking. That's not how we normally draw it. We would draw it N, 1, 2, 3, triple bond, and then put the lone pairs outside. So this structure has how many lone pairs? 2. And how many bonding pairs? 3. 3 bonding pairs. When we're looking at, How many valence electrons does each of the atoms have? Do they have the octet? Are they happy? This nitrogen is going to count all of the bonding electrons. Each line is 2. 2, 4, 6, 8. And maybe green. The other nitrogen is also counting these 2, 4, 6, 8. Okay? So Lewis theory, you get a lot of counting by 2s to 8. Any questions? So the Lewis model predicts that water is stable, H2O, and that H3O is unstable. So let's look at those. We've already drawn the Lewis structure for water, so we're not going to go over the details of that again. So there's H2O. Hydrogen has a duet. Oxygen has an octet. Everyone is satisfied. Let's look at H3O. So an oxygen and 3 hydrogens. So each of the hydrogens has a single electron, and the oxygen has 6 electrons. So if we're going to share, the oxygen and the first hydrogen can share an electron, and the oxygen and the second can share an electron. But now oxygen has 8. It doesn't want 9. That's too much. Can't handle it. So oxygen's not going to share with this other hydrogen, which predicts that H3O doesn't exist. And it doesn't. It doesn't form. It just doesn't. What about H3O plus? How would this become a positive ion? By losing an electron, right? So if we took an electron away, now this overall has a positive charge. Now, because the oxygen lost an electron, it can share with that third hydrogen. And that's called the hydronium ion. And that is pretty stable. What about H2O2? That's hydrogen peroxide. Each oxygen has 6 valence electrons, each hydrogen has 1. So the hydrogen can share with one of the oxygen, with one of the hydrogens, and then share with another oxygen. And that other oxygen can also share with hydrogen. And they can get octets for the oxygens and duets for the hydrogens. And hydrogen peroxide exists. Any questions? So we know that covalent compounds have individual molecules. They're not just a lattice of alternating ions. They're discrete molecules. And the reason for this is that those covalent bonds are highly directional. When oxygen and hydrogen are sharing those electrons are between the oxygen and the hydrogen. They're not off on the other side somewhere. And so we have this bond between those two atoms. So the example here is looking at pentane. So in pentane, you have five carbons and 12 hydrogens, and they're going to be covalently bonded together, which is going to hold each molecule together but the molecules are not going to be bonded to the other molecules. There's going to be some weak intermolecular forces that we'll learn more about later. Those are very weak forces. And as a result, pentane has a very low boiling point. And it will go into the gas state. These molecules, because they're not tightly held by the other molecules, are just free to kind of literally float away. So we have weak forces between the molecules, and that gives molecular compounds, covalent compounds, lower melting and boiling points than ionic compounds.